Hello everyone. In this video we'll begin our discussion of how to analyze an IR spectrum. And we're going to start with a very specific region of the IR spectrum, what's called the hydrogen region. So this is between 4000 and 2700 wave numbers. And so this is the far left-hand side of the IR spectrum if you're looking at it. The reason why we're interested in this particular region, why we're starting here, is many organic compounds contain bonds to nitrogen. So at the end of this video, hopefully we'll be able to identify a variety of functional groups by looking at a structure. So we can identify an alkane, an alkene, an aromatic ring, an alkyne, an alcohol, and an amine, and be able to take a look at an IR spectrum and identify the various peaks associated with those functional groups. So to begin with, we can break down IR spectra by taking a look at various different regions. So depending on the strength of the different bonds, we're going to see peaks in different regions of the spectrum. So again, in this video, we're going to focus mainly on bonds to hydrogen, but there are various different regions that we can identify, such as the triple bond region, the double bond region, and then single bond region. And if we look at the axis, the x-axis for our IR spectrum, this is in what's called a wave number. So this is a little bit convoluted and a little bit based in historical reasoning, but essentially what it is the inverse, so 1 over the wavelength of light. So again, when we're talking about IR spectroscopy, we're focusing on a very narrow region of the electromagnetic spectrum. So the wavelength of that is incorporated here in the x-axis, and it's in centimeters. And so that's why our unit is in centimeters to the -1, or reciprocal centimeters. So we can also break down the IR spectrum into parts that we're really going to focus on interpreting, and then parts that we're not going to. And ultimately, these are what's called the diagnostic region and the fingerprint region. So the diagnostic region, similar to the way in which a doctor diagnoses a condition based on a variety of different symptoms, what we're going to do is focus on this particular region and take a look at various different peaks that occur in that region. And then from that information, figure out essentially what functional groups we have in our molecule. The fingerprint region is going to be a lot messier, especially as our organic molecules get larger and larger. So we're not going to focus a ton of time on sort of identifying individual peaks in that particular region. But what we can do is, if we have a spectrum that we know of a particular compound, we can compare that to an experimental spectrum. So if we collect an IR spectrum in the lab, we can compare that to an existing spectrum, and just like a fingerprint, the peaks in that region should overlap. So this will help us to say that, okay, conclusively, this is the compound that is created or isolated. So with that, IR spectroscopy tells us essentially what functional groups exist in your molecule. And this can be important if we're isolating or trying to purify different molecules. So that should contain just the functional groups of our desired compound. And then later in the semester, when we talk about reactivity, what we're doing is essentially converting one functional group to another functional group. So we can take an IR spectrum of our product and identify whether that reaction occurred or not. So to start with, here is our simplest functional group, which we call an alkane. An alkane contains just carbon-carbon single bonds and carbon bonds to hydrogen. So in each of these spectra, I'm going to delineate the diagnostic and fingerprint region with this dotted red line. Again, mainly we'll focus on the hydrogen region here, which is above 2700 reciprocal centimeters. So if we look at this spectrum here, we see a very large peak here. We see multiple peaks, one at 2971, one probably at about 2900, and one at 2863. And so these are corresponding to absorption at or stretching of the carbon-hydrogen bonds in these particular molecules. And the reason why there's multiple peaks, there's not just one peak, is there are different bond strengths of these various different carbon-hydrogen bonds. But importantly, if we have an alkane, all of the peaks will occur between roughly 3000 and 2850. The second functional group that we'll talk about is an alkene, and an alkene must contain at least one carbon-carbon double bond. So we can say that there is an alkene functional group in our molecule, again, if we have a carbon-carbon double bond. And so if we focus on the hydrogen region, we see a new peak that appears above 3000, so in a different region than we saw for our alkane. And the reason for that is we have different hybridized carbons. So all of these carbons here are sp3 hybridized, whereas the two carbons that make up our alkene are sp hybridized. So the bond length between the carbon and hydrogen of the carbon sp2 versus the carbon sp3 CH bond are different. And so we have a different sort of peak in our IR spectrum. So typically, if we have a carbon sp2 hybridized carbon CH stretch, that will occur again above 3000, roughly to about 3150. Another important motif that we'll see frequently in organic chemistry is an aromatic ring. And again, the most popular one is a benzene ring. And so I just wanted to point this out as well. So a benzene ring contains 3 carbon-carbon double bonds, and specifically we call an aromatic ring if it is a 6-membered ring with 3 double bonds in it. So notice that we have a lot more peaks that are above that 3000. So again, multiple peaks above 3000 that correspond to the various different carbon-hydrogen stretches of, in this case, toluene. So everything that occurs above 3000 is the carbon sp2 CH stretch. Notice that we have one carbon that is sp3 hybridized. So we do have one peak or a couple of peaks that are below that 3000. So again, we can delineate between the sp2 and the sp3 hybridized carbon CH stretches based on where they are on the IR spectrum. The last bond from carbon to hydrogen that we'll discuss is an alkyne. So an alkyne is a molecule that contains at least one carbon-carbon triple bond. And if we're focusing specifically on the hydrogen region, we're interested in what's called a terminal alkyne. And so that is if the triple bond is at the beginning or end of the molecule. The reason for that is we have to have a sp hybridized carbon that is bound to a hydrogen, right? If we had what's called an internal alkyne, if the triple bond is in the middle of the molecule, we don't have a sp hybridized carbon attached to a hydrogen. And so with the sp CH stretch, we see again the IR peak shifting even further to the left. So typically a carbon sp CH stretch is between 3300 and 32 reciprocal centimeters. So here's just a kind of quick overview of the alkene, the alkane, and the alkyne. So notice that as we go from sp3 to sp2 to sp, the peaks become larger in terms of their wave numbers, so they shift further to the left. And this is important for us to be able to identify because many organic molecules are going to have at least one carbon-hydrogen stretch in them. So this is something that will be pretty much in every single molecule that we analyze via IR spectroscopy. Now moving away from carbon-hydrogen to other atoms. So if we take a look at the bond between oxygen and hydrogen, if we have a bond that looks like this, or a molecule that looks like this, we call that an alcohol. So that has a carbon bound to an oxygen and an oxygen bound to a hydrogen. So this is our functional group. And then we're going to introduce a convention. This is called an R group. So an R group basically refers to the rest of the molecule that is not the functional group. So oftentimes in your book and in other resources that you utilize, you'll see an R and some sort of functional group attached to it. The R typically corresponds to the rest of the molecule, which is typically contained of carbons and hydrogens. So if we look at alcohols are pretty easy to identify in the IR spectrum because they have this very broad and very strong peak in this region of the IR spectrum. So notice that this is pretty easy to identify. It's kind of the largest peak that we see just looking at the IR spectrum. So this corresponds to the stretch between the bond oxygen and hydrogen. And notice in the hydrogen region, we also have, again, CH stretches, and these correspond to sp3 hybridized CH stretches. Again, they're below 3,000, and that is consistent with these two sp3 hybridized carbons. The last functional group we will talk about is an amine, and an amine contains at least one carbon nitrogen single bond. And so there are various different types of amines, and that's based on the number of carbon-nitrogen bonds. So we can have what's called a primary amine, which has one carbon-nitrogen bond. We can have a secondary amine, which has two carbon-nitrogen bonds, or a tertiary amine, which has three carbon-nitrogen bonds. And in terms of analyzing the hydrogen region, we're only going to be looking at primary and secondary, because those are the only one that contain nitrogen-hydrogen bonds. So if we look at this example compound here, aniline, we notice that it is a primary amine. So it has one carbon-nitrogen bond, and the remaining two bonds that nitrogen has are to hydrogen. And so we notice that we have these broad peaks, and we have two of them. So since we have two nitrogen-hydrogen bonds, we have two stretches in our IR spectrum in the hydrogen region corresponding to that amine. If we were to have a secondary amine, we would only have one peak in this particular region. And again, if we have a tertiary amine, we have no nitrogen-hydrogen bonds, so we would not have anything appear in this region of the IR spectrum. So here is just to quickly review what we talked about in the video. Again, these are general regions for the IR spectrum. So sometimes there are exceptions to these, but again, typically these are where the peaks for the corresponding functional groups reside.